What if a particle could be its own evil twin?
Ooh, that's a good one.
That's the kind of mind-bending idea we're going to dive into today.
All right, I'm ready.
Majorana Fermions.
Oh.
These theoretical particles,
hmm
if they exist, would completely change how we understand the universe.
Yeah.
Quantum computing,
hmm
the mysteries of neutrinos,
Right.
these elusive particles could be the key to unlocking some of science's biggest questions.
Absolutely.
So strap in, folks. It's going to be a wild ride.
It's a journey that started almost a century ago
Wow.
with Ettore Majorana.
Okay.
He proposed the existence of these strange particles back in 1937.
Wow, 1937.
Yeah,
So almost 100 years ago.
that's right. But even after decades of research, we're still searching for that definitive proof.
And that's what makes it so fascinating, right?
Oh, absolutely.
We're on the edge of a scientific revolution.
Yeah, it's really exciting.
But before we get too far ahead of ourselves, let's make sure we're all on the same page. We know that most particles have an antiparticle,
Right.
like an electron and its opposite, the positron.
Exactly.
Same mass, but opposite charge.
Like matter and antimatter, always locked in this cosmic dance of creation and annihilation.
Right. But a Majorana fermion, it's theorized to be both particle and antiparticle at the same time.
Yeah.
It's like looking in a mirror and seeing
Yeah.
still you.
It really challenges like our fundamental understanding of physics.
It does. And it all boils down to a pretty fundamental equation in particle physics, right?
Yes.
The Dirac equation.
The Dirac equation, yeah.
Okay, I'm sure some of our listeners are familiar with that one.
Sure.
But for those who aren't, could you give us like a quick jargon-free explanation?
Of course, of course.
Mm.
Imagine the Dirac equation as like the rule book governing how these tiny particles behave
Okay.
at super speeds.
Mhm.
It's a set of equations that combine quantum mechanics with special relativity.
Okay.
And it's really the foundation for our understanding of fermions.
Fermions being particles like electrons, protons, neutrons.
Exactly. The building blocks of matter.
Right.
But here's where it gets interesting.
Okay.
The Dirac equation, it allows for a special case,
Okay.
like a loophole,
Okay.
where a particle could be its own antiparticle.
Oh, so the rulebook itself hints at the possibility of this mind-bending concept.
Precisely. By removing certain phase factors, the math suggests that a particle could, in theory, be its own mirror image.
So we have this theoretical possibility.
Yes.
This tantalizing hint from the math.
Mm-hmm.
But where do we actually see Majorana fermions in the real world?
Well, that's the million-dollar question.
Right.
We haven't found fundamental Majorana particles just floating around in space yet.
Okay.
But there's another approach.
Okay.
One that involves creating them here on Earth.
Wait, creating them?
Yeah.
How is that even possible?
That's where the fields of particle physics and condensed matter physics kind of converge.
Okay.
It's like building a tiny controlled universe.
Within a material
Yeah.
where these exotic particles can emerge.
So not discovering them, but engineering them.
Exactly,
Yeah.
exactly.
Okay.
And one of the most promising avenues for this is a theoretical model called the Kitaev chain.
The Kitaev chain. Okay, I'm intrigued.
Yeah.
Break it down for me. What exactly is the Kitaev chain?
Sure.
And how does it relate to creating Majorana fermions?
So imagine a line of atoms,
Okay.
like a chain reaction,
Okay. Yeah.
waiting to happen.
I can picture that.
Now, in this chain, each atom is a site where an electron can exist.
Mm-hmm.
And the Kitaev chain model, it describes how these electrons, which are fermions, can hop between sites
Okay.
and interact with each other
Mhm.
under very specific conditions.
So we've got our chain of atoms.
Yeah,
Our electrons are jumping between them.
right.
But how does this lead to Majorana fermions?
Think of it like this. You have this chain of atoms,
Sure.
and at the very ends of this chain,
Yeah.
under the right conditions.
Something extraordinary emerges.
Okay.
Those conditions involve fine-tuning the interactions between electrons,
Okay.
creating a specific type of environment.
And that environment gives rise to.
Majorana fermions.
Wow.
The Kitaev chain model predicts that these elusive particles will pop up at the edges of the chain,
Okay.
like bookends, holding the whole system together.
So we're not trying to smash particles together to create a Majorana fermion.
No.
We're manipulating a system at the atomic level to make these particles appear.
Exactly. It's a testament to the power of condensed matter physics. We're not just observing particles, we're manipulating them, engineering environments to potentially create entirely new forms of matter.
Okay, now I'm really starting to see the potential here.
Yeah.
We've gone from this abstract theoretical concept to a tangible, if incredibly challenging, experimental pursuit.
And that pursuit is happening right now in labs around the world. Scientists are using incredibly tiny wires called nanowires.
Okay.
They're often made of semiconducting materials. Nanowires.
Yeah.
So we're talking about structures that are billions of times smaller than a human hair.
You got it. And by combining these nanowires with superconductors and applying magnetic fields, they can create conditions that mimic the Kitaev chain.
Oh, so it's like building a miniature racetrack for Majorana Fermions.
A very, very tiny racetrack. But
Yeah.
here's the catch.
Okay.
Distinguishing true Majorana fermions from other quantum phenomena that might look similar in experiments is a massive hurdle. It's like trying to find a specific grain of sand on the beach.
That's a good analogy.
There's a lot of debate and scrutiny in the field, as you can imagine.
It sounds like an incredibly difficult task.
It is, yeah.
But the potential payoff must be enormous.
Oh, it is. If scientists can definitively prove the existence of Majorana fermions, especially those created in these engineered environments, it would be a monumental discovery with implications far beyond just particle physics.
Okay, now I'm even more on the edge of my seat.
Right.
What are those implications?
Yeah. Well, one of the most exciting possibilities lies in the realm of quantum computing.
Quantum computers.
Right.
Now we're talking. What's the connection between these exotic particles and the future of computing?
It all comes down to a remarkable property of Majorana fermions, non-abelian statistics.
Okay, I'll admit that sounds a bit intimidating. Can you break it down for us?
Sure. Imagine braiding hair.
Okay.
The order in which you braid the strands matters, right?
Yeah.
Swap the order, you get a different braid.
Makes sense.
With Majorana fermions, something similar happens. When you exchange them, the system's wave function changes in a way that depends on the order of the exchange.
Okay.
That's what we mean by non-abelian statistics.
So it's like they remember how they were braided.
Yeah.
And that information is encoded in the system.
Precisely.
Yeah.
And this memory makes them incredibly valuable for quantum computing.
Because the information is stored in the way they're arranged.
Yes.
Not in the particles themselves.
Exactly. And that's the key to building more robust quantum computers.
Okay.
Current qubits, the building blocks of quantum computers, are very fragile, prone to errors.
Yeah.
But Majorana fermions could potentially solve this problem.
Because they remember their history.
Yes.
They're less likely to be disrupted by outside noise, making them more stable.
That's the idea.
Yeah.
This is the dream of topological quantum computing.
Wow.
Using the braiding of Majorana fermions to create qubits that are inherently protected from errors.
So we've gone from this abstract concept of a particle being its own antiparticle to the potential for building a revolutionary new type of quantum computer.
Right.
It's amazing how interconnected these ideas are.
Yeah, it really is fascinating.
But I have a feeling this is just the tip of the iceberg.
You're right. The potential of Majorana fermions extends far beyond quantum computing.
Oh.
They might even hold the key to solving some of the biggest mysteries in cosmology.
Okay, now you've really got my attention. Tell me more.
Remember those ghostly particles we talked about earlier?
You mean the neutrinos?
Yeah, the ones that are constantly streaming through us?
Yeah, the ones that are so lightweight
Yeah.
and elusive, they can pass through the entire Earth
Right.
without even noticing.
It's amazing.
I always found them a bit spooky, to be honest.
Well, get ready for things to get even spookier.
Okay.
Physicists believe that neutrinos might actually be Majorana fermions.
Hold on. So these particles, born in the hearts of stars and flung across the universe, could be their own antiparticles.
That's right.
That's next level mind-blowing.
It really is. And it has profound implications. If neutrinos are indeed Majorana fermions, it could explain some of their most puzzling characteristics.
Okay, like what?
For instance, why are they so incredibly light compared to other particles?
I'm all ears. This is really making me rethink what I thought I knew about the universe.
It's a journey of constant discovery. And the connection between neutrinos and Majorana fermions is a prime example of how seemingly disparate areas of physics can intertwine.
Okay.
But how could we actually prove that these cosmic travelers are their own antiparticles?
Yeah, that seems like a tough one. Neutrinos are already notoriously difficult to detect.
True, but not impossible.
Okay.
One way to prove it would be to observe a process called neutrinoless double beta decay.
Neutrino-less double beta decay.
Neutrino-less double beta decay. Okay, that sounds a bit complicated.
Sure.
Could you unpack that for me?
In normal double beta decay, two neutrons in an atom simultaneously decay, transforming into two protons.
Mm-hmm.
In the process, they release two electrons and two antineutrinos.
Okay, so it's like a tiny nuclear transformation happening within an atom.
Precisely. But here's where the Majorana twist comes in.
Okay.
If neutrinos are their own antiparticles, then those two antineutrinos produced in the decay could annihilate each other.
Wait, so it's like they cancel each other out,
Yeah.
leaving behind a very specific signature.
Yep. A kind of fingerprint that scientists could detect.
Exactly. Observing this neutrino-less double beta decay
Yeah.
would be the smoking gun. The undeniable evidence that neutrinos are indeed Majorana fermions.
So is anyone actually looking for this? It sounds like an incredibly difficult experiment.
Oh, absolutely. There are numerous experiments worldwide using incredibly sensitive detectors, often buried deep underground to shield them from cosmic rays and background noise.
Wow.
They're searching for this rare event, this whisper of a signal that could rewrite our understanding of the universe.
Wow. It's amazing to think that scientists are out there,
Yeah.
literally digging deep into the earth, trying to catch a glimpse of these elusive particles.
It's a testament to the power of human ingenuity and our relentless pursuit of knowledge.
It really is.
And the search for Majorana fermions has led to a whole new way of thinking about the phases of matter.
Phases of matter.
Yeah.
I thought we had that covered. Solids, liquids, gases. What else is there?
Well, those are the classic phases
Right.
we learn about in school.
Right.
But in condensed matter physics, especially at extremely low temperatures,
Okay.
things get a lot more exotic.
So, like, close to absolute zero.
Exactly.
The point where all molecular motion stops.
Yeah, and one of the most intriguing phases is called a topological phase.
Okay, a topological phase. That sounds pretty abstract.
It is, but let me try to explain it in a way that connects to something familiar. Imagine a donut and a coffee mug.
Okay, two of my favorite things.
They look very different, right?
Yeah.
But topologically speaking, they're equivalent.
Oh, okay.
They both have one hole. You could deform one into the other without tearing or gluing.
So it's about the overall shape.
Yes.
The fundamental structure rather than the specific details.
Precisely. Topological phases of matter are defined by their global properties, not their local details. They exhibit unique characteristics that arise from the overall topology of the system.
Okay.
And this is where Majorana fermions come in. Yeah. They're predicted to exist at the edges or boundaries of certain topological phases of matter.
So it's like those bookends we talked about with the Kitiev chain.
Exactly.
They're not just random particles floating around. They're fundamentally connected to the topology of the material.
Yeah, they're called topological boundary states.
Okay.
And they're incredibly robust. You can't destroy them without changing the topology of the system itself.
So they're protected by the very structure of the material.
That's right.
That's pretty cool.
It is, and it has profound implications for quantum computing.
Right.
If we can harness these Majorana fermions, we could potentially create qubits that are incredibly resistant to errors.
Because the information is encoded not in a single particle,
Right.
but in the topology of the system itself.
Exactly.
Making it much harder to disrupt.
Precisely. It's a whole new paradigm for quantum computing.
Wow.
One that takes advantage of the deep connections between topology and quantum mechanics.
So, by studying Majorana fermions, scientists are not only exploring new particles, but also delving into a whole new way of understanding the very fabric of matter itself.
It is. It's like opening a door to a whole new universe of possibilities.
It really is.
It's a truly fascinating journey, and it's only just beginning. There's so much more we're learning about topological phases of matter, and it's all thanks to the quest for the Majorana fermion.